Very good evening to all. Audio video clear है बेटा? Now audio video is clear? Yes. Audio video is clear? Very good afternoon. Yadunath, very good evening. Very good evening, dost. Please like the session and share as much as possible. In last class, we discussed substring. Substring. So what is the definition of substring? What is the definition of substring? Any consecutive sequence of symbols, any consecutive sequence of symbols over the given string. Isniya Jadon, very good evening. Over the given string. For example, we have a string W, TOC. So how many number of substrings are possible? Epsilon, T, O, C, TO, OC, TOC. So number of strings are 7. If length of the string is 3, then number of substrings are 7. Clear? Is it clear? Yes, my dear friends, this one is clear. So next example, find out the substring of Yadu. Find out the number of substrings for given string Yadu. Please find out. Find out the number of substrings for the given string Yadu. Find out the number of substring of Yadu. See, epsilon, Y, A, D, U, Y, A, D, D, U, Y, A, D, A, D, U, Y, A, D, U. How many number of substrings? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Clear? 11. If length of the string is 4, then number of substrings 11. Now, find the number of substrings for this FP. Find the number of substrings for FP. Find the number of substrings for AP. Yes. Do fast. Yes. What is the answer for this one? C. Epsilon A P Y AP PP PY A double P double PY A double PY. So count the number of substrings 4, 5, 6, 7, 8, 9, 10. So we can get 10. The length of the string is length of the string is 4 and we can get 10 substrings. Length of the string is 4, we can get 11 strings. So can we generalize for this? Can we generalize this? Yes, we can generalize this. See. Note, this question asked in GATE 2-3 times. If the length of the string, if the length of the string is n, then the maximum number of substrings possible, maximum number of substring possible equal to n into n plus 1 divided by 2 plus 1. This one because of null string. Okay. So see, in first example we have length 3 and each alphabet is unique. Each character is unique. Whenever a character is unique in a string, the number of substring equal to n into n plus 1 by 2 plus 1. If the character is repeated, then number of substrings less than this. Clear? So see the first example, we have a string W, TOC and each and every character is unique. That's why we can get 3 into 3 plus 1 divided by 2 plus 1. So this one is 2, 7. Next string is Yadu. Each character is unique. That's why we can get 11 number of strings. 4 into 4 plus 1 divided by 2 plus 1. 11. But in the case of this string, P is repeated 2 times. That's why we can get 10. Because P is repeated 2 times. Clear, my dear friends? The concept of substring is clear. Yes or no? Okay. Next, trivial substring. trivial substring. Trivial substring. Null string and string itself is known as trivial substring. Trivial substring. Trivial substring. Note, trivial substring always 2. Trivial substring always 2. Next is non-trivial substring. Non-trivial substring. Except null and string itself, except null string and string itself is known as non-trivial substring. Non-trivial substring. Non-trivial substrings. Okay. Note, if the length of string is n, then number of non-trivial substring maximum equal to n into n plus 1 divide by 2 minus 1. Clear? Is this clear to you? Clear? Yes. Is it clear? Reply fast. Okay. Now, next concept, prefix. Prefix. So, what is prefix of a string? What is prefix of a string? What is prefix of a string? Any leading symbol of a string is known as prefix of a string. Any leading symbol of a string is known as prefix of a string. For example, string W is TOC. Then what is the prefix of TOC, epsilon, T, TO, TOC. These are the prefix of TOC. So what is the conclusion from here? If the length of a string is n, then number of prefix equal to n plus 1. N plus 1. Clear? This one is clear to you? Next, suffix. This one, prefix is clear? Next, suffix. Any tailing symbol, of a string is known as suffix of a string. Suffix of a string. Suffix of a string. For example, TOC. So what are the suffix of TOC? Epsilon, COC, TOC. Okay. So same note here. If length of a string is n, then number of suffix equal to n plus 1. Clear, friends? This is clear? So these are the basic terminology for theory of computation. Clear, friends? Shall we move on? Okay. See some another terminologies. What is state? What is transition? Initial state and final state. See, what do you mean by the state? State is represented by the circle. If we have two circles and we have some edges between circles, these are known as transitions. What do you mean by the initial state? Initial state is represented by the arrow. What is final state? Final state represented by the double arrow, or sometime it is represented by the star. Okay. Clear? Okay. Now, another term is sigma star. This is known as clean closure. What is this? Sigma की power 0 union sigma की power 1 union sigma की power 2 union and Sigma star is known as universal language. Universal is known as universal language. We'll see what is language. Wait for some time. Sigma star is known as universal language. Universal language. This, because of this, it contains null string or epsilon. This is the 0 length string, this is the 1 length string, this is 2 length string. Now, another term is sigma ki power plus. This plus is known as positive closure. Positive closure. Closure. What is sigma ki power plus? It is start 1 length string. It is a combination of 1 length, 2 length, 3 length and so on. So sigma ki power 1 union sigma ki power 2 union sigma ki power 3 union dash dash. So what is the relationship between this? Sigma plus equal to sigma star minus null string. This is the relationship between positive closure and clean closure. Clean closure. Clear? Don't worry, CP 107 सब कुछ मिलेगा. Don't worry. You will get each and everything. Okay? We'll solve each and every previous year question. Okay? Wait. Now, what is language? What is language? What is language? What is language? Set of strings. Set of strings. Language is set of strings. It can be finite, it can be infinite. For example, this language contain only null string. So this is non-empty finite language. Non-empty finite language. Finite language because it contain only one string. L2. Epsilon A, B, AB, BA, AA, double B. This is also finite. This is also finite. So this is known as finite language. Finite language. Finite language contain only finite number of strings. Okay. Next. This is empty language. Empty language. Empty language. Next, if sigma is a comma b, then epsilon a, b, double b, ab, ba. This is infinite language, any combination of a's and b's. Infinite language. So these are the basic concepts or basic terminology that we will use in further lectures. Everything is clear to you? Yes? Clear? Clear? Next, chapter 1. Chapter 1. Finite Automata. Why it is called finite automata? See, the word automata is taken from the Greek word automation. Automation. Automation is the singular word and automata is the plural form of automation. What is the meaning of automation? Self-acting. Self-acting, or something happen automatically, or we can say abstract machine, or we can say abstract. What do you mean by the abstract? Some information hidden from the user, only useful information given to the user. Suppose AC gives you ठंडी हवा, ओके AC जो है वो आपको ठंडी हवा देता है, लेकिन how it work internally we don't know, and we don't have any query about this, how it works internally. So these are the abstract machine. Automata means self-acting, or something happen automatically. And what is the meaning of finite? It have finite memory. It have finite memory. Clear? Now, finite automata we classified into two categories, or this is also known as discrete automata. Discrete automata. We classified finite automata into two categories: without output, without output, self-acting. Yes, Amit, self-acting. Without output. And another classification is with output. With output. Without output is also known as acceptors. Acceptors. It means they accept something and they reject something. These machines are accept something and something is something reject. And what is with output? These are known as transducer. Transducer. We will give some input and they produce some output. That's why it is known as with output. Without output again classified into three categories: deterministic finite automata, non-deterministic finite automata, null moves, or we can say epsilon and FA. The power of all these three are same. Whatever we done by DFA, this is also done by NFA and epsilon NFA. That's why the power of NFA, DFA and epsilon NFA are same. Now, with output again classified into two categories. Two categories. Murray machine, Mealy machine. Again the power of Murray machine and Mealy machine are same. So we will discuss each and everything one by one. Clear, my dear friends? Please note this. Clear? Clear? Okay. Now, see the structure of finite automata. Structure of finite automata. Finite automata have infinite tape, this infinite tape divide into cells. Each cell contain only, or we can say at each cell contain at most one character, only one character. We have read head, initially it is denoted the first character of the string. This input tape contain the input is a string, and the another end of this read head is connected by the finite control or we can say finite state control mechanism. Finite state control mechanism. It hold current state. Clear? It is store current state of finite automata. This is the structure of finite automata. So first we will see deterministic finite automata, DFA. Deterministic finite automata. We have two terms, deterministic and non-deterministic. What do you mean by the deterministic? Deterministic means we have exact information. What do you mean by the non-determinism? We check all the possible possibilities, or in deterministic we have exact information. So what is the definition of DFA, deterministic finite automata? See, each and every state have exactly one transition, on every input symbol. Each and every state have exactly one transition on every input symbol. Clear? Mathematically it is defined by 5 tuple. M defined by 5 tuple. Capital Q, sigma, Q naught, delta, F. So what is Q? Set of finite states. Sigma, input alphabet. Input alphabet. What is Q naught? Initial state. We have only one initial state. In finite automata, we have only one initial state. Next, F, set of final state. It means we have more than one final state in one finite automata. Set of final states. F is a subset of Q. Now, delta is transition function. What do you mean by the transition function? Is it defines the rules how machine takes move, how machine take moves. Transition function. Transition function. So delta is defined in deterministic finite automata Q. For every input symbol, we have exactly one state. We have exactly one state. Each and every state have exactly one transition on every input symbol. Suppose we have Q, we have two states, Q0 and Q1. Input alphabet is A and B. So what do you mean by this? This is the set of Q, and this is set of or we can say, wait, Q cross sigma. So we have Q0, Q on A, Q0, B, Q1 on A. We have these possible combinations. So it will move exactly one state. Either it goes to Q0 or it goes to Q1 or it goes to dead state. We'll see what is the dead state. What is the dead state? Or we can represent like this. We have this set and we have another set that contain only two states, Q0, Q1, Q0, Q1. So this either goes to this or this one. Only one state, only one state. So this is the representation of DFA. This is the representation of DFA. Clear? We'll see one example. This definition is clear to you? Yes? This definition is clear? Tell me fast. Fast reply. This definition is clear? Yes, Yadunath, Amit, CP107, this definition is clear to you? Okay, see example. We have a fan, example, we have a fan. The example of fan. The input for this fan is either 0 or 1. Either it is off or on. So this fan have initial state Q0. This is the off state, suppose. And this is the another state Q1. This one is final state when fan is running. When fan is running. Suppose we have two input symbols. So each and every state have exactly two transitions. One for 0 and one for 1. If I give 0 onto this fan, then this fan is continuously off. Continuously off. It means this is the initial state. If I give to 1, input 1 on initial state, then it will start and it will running. See, this is the running. Now, Q0 have exactly one transition on every input symbol. See how to write the transition. Q naught on 0, it goes to Q naught. Q naught on 1, it goes to Q1, exactly one state. Now, we are in the final state. We are in the final state. Here, fan is running. If I give input 1 to this state, then it will continuously running state. If I give input 0, then it will goes off condition. See, this is DFA or not. Each and every state have exactly one transition on every input symbol. So Q naught have exactly one transition for 0, exactly one transition for 1. Q1 have exactly one transition on 0, it will goes Q naught. Q1 on 1, it will goes Q1. So this is the example of DFA. This is the example of DFA. Now, this is known as state diagram. State diagram. Another representation is known as transition table. Transition table. So how to represent this state diagram into transition table? See, we have two input 0 and 1. Here we write input and row wise we write state. So we have initial state Q naught. Q naught on 0, it goes to Q naught. Q naught on 1, it goes to Q1. Q1 on 0, it goes to Q0. Q1 on 1, it goes to Q1. And this is the final state. So either we mark as a star or with circle. With circle. So this is the transition representation of this state diagram. Both are same. Both are same. Either we represent with the help of a state diagram or with the help of transition table. So my dear friends, this is clear. This is clear to you. Yes. Clear? Shall we move on next topic? This is clear. Okay. Now, we'll see some example based on DFA. Listen carefully. Listen carefully. For every language, we have infinite number of DFA. For every language, we can construct infinite number of DFA. So for every language, we don't have unique DFA. But minimal DFA is unique for every language. Minimal DFA is unique for every language. Minimal DFA is unique for every language. I repeat, minimal DFA is unique, but we can construct infinite number of DFA for any language. Clear? What do you mean by the minimal DFA? Those DFA which contain minimal number of states is known as minimal DFA. So our first example, construct a minimal DFA for the language which contain which contain any combination of A's and B's, including null string, including null string. So see, there is a concept acceptance. There is a concept of acceptance. So what do you mean by the acceptance? When we read a string, from initial state and it ends with the any one of final state, when it ends with any one of the final state, then we can say this string is accepted by the given DFA. Otherwise it is rejected. Clear, my dear friends? So first you write the language for the given question. In given question, what is the input alphabet? A comma B. So language contain epsilon, any combination of A's and B's, including epsilon, single A, single B, double A, double B, AB, BA, any combination of AB, So listen carefully, my dear friends. Whenever language contain epsilon, then always initial is final. Always initial is final. Now it contain any combination of A's and B's, so we can make a loop with A or B. We can take any string with the combination of A and B. Suppose we have a string AB. So how it will work? Initially we read A on Q0, and read head is move here, and it will read and change the state Q0, and it will read B. And there is a string end, and it is on final state. So this is the minimal DFA for this language. If minimal is not given, see, we can write this DFAs also. This is also DFA for this language. We can make infinite number of DFAs, but minimal DFA is unique. Is it clear? Yes, this question is clear. This question is clear. Okay. See the next question. Construct a minimal DFA that accept all strings of A's and B's where each string start with A. Start with A. Start with A. Try to solve this question. Try to solve this question. First, you write the language for this. After that, construct a minimal DFA. Try to solve this question. Okay. See the language. See the language. What is the language for that? The minimum length of a string is A because it always start with A. Next is AB. Next is AB, AAB, ABB, and so on. So what is the minimum length string? Minimum length string is this. So first you construct the skeleton for this string. First you construct the skeleton for this. So this is the initial state, Q0. Whenever we read A on initial state, it goes to the final state. Why? Because our language contains this string. If languages contain this string, then finite DFAs accept this string. So this is our skeleton. This is our skeleton. After A, any number of A's and B's are possible. So we make a loop on this state. Now, check, this is the DFA or not? No, this is not a DFA. Why? Because the definition of the DFA is each and every state have exactly one transition on every input symbol. So here Q0 have only one transition on input symbol A, but it does not have any transition on B. So what is the possibility of B? We cannot make the loop of B on Q0. Why? If I make the loop, then it will start with A. Whenever B come in starting position, then it goes into the another state, or this state is known as dead state or trap state. Whenever B come before A, it always goes into the dead state. So this machine never respond those strings which start with B. Clear? So this is the DFA for given language, minimal DFA for the given language. Is it clear? Is it clear? Yes, friends? Yadunath, dead state means trap state. If I give B initially, then this machine does not give any response to you. That's why it is called dead state. Okay? Clear? See the next question. Construct a minimal DFA that accept all string of A's and B's where each string end with A. Each string end with A. Where each string end with A. Please try to solve this question. Clear? Yes? Have you done this? See, what is the language for this question? End with A. So minimum length of the string is A. Double A, B A, B A A, B B A, and many more. Now, first you construct the skeleton for minimum length string. This is our initial string. When we read as input A, it goes into the final state. Now, this is our skeleton. Now make the DFA for this one. Make the DFA for this one. So, what about the B on Q0? We can make the loop B because it can contain B, 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 A. So Q0 have one transition for A and one transition for B. Now come to the Q1. Whenever A come, it is on Q1 state. These strings are accepted, end with A. Now, what about this A, B, A? Whenever B come on Q1, it goes to the Q0. So check, this is the DFA for the given language. Clear, my dear friends? Clear? Clear? Is it clear to you? Have you any doubt? Give me a fast reply. Okay. So today class is finished. In tomorrow class we will discuss more example based on the DFA. Clear? Clear, friends? So thank you so much. Shubh Ratri, Jai Mahakal, Jai Hind, Jai Maa Bharati.